decentralization occurs. That is, generation is decentralized. That is distributed decentralized generation. So those are the three buzzwords that we normally encounter in modern power system operation. This coupled with electrification. Electrification is another important terminology that we come across. That is electrifying all, especially industrial operations, all operations. Suppose if we electrify, then the coal and natural gas need not be burned for generating heat and other things for different processes, that is industrial processes, and we can decarbonize the particular sector, industrial sector. In fact, hard to electrify sectors are there in the industry, that is cement manufacturing, then iron and steel sector, then petrochemical sector, aluminum sector, refineries, etc. They are all hard to electrify sectors, and we have to have special care for hard to electrify sector in our decarbonization drive. Then only we can achieve total elimination of carbon dioxide that emitted to the atmosphere, and greenhouse gas effect can be reduced, and atmosphere can be decarbonized, and the sector itself can be decarbonized. So for deep decarbonization of the power sector, we are coming across, now we have limiting our interest to the power sector. For deep decarbonization of the power sector, emissions from power sector should be stopped. That is, coal and natural gas, the usage of coal and natural gas for generation of electricity has to be stopped. Fossil-based generation must be transformed to renewable-based generation. Then carbon dioxide already present in the atmosphere should be absorbed either by natural means or by synthetic transformation. We can have a carbon sequestration, that is, industries emitting carbon dioxide. At the point of emission, we can collect carbon dioxide, store it, and use it for other industrial processes. That is, we stop the emission of carbon dioxide. That is called carbon sequestration. So carbon sequestration can be undertaken, and it can be used for other industrial purposes, carbon dioxide applications of carbon dioxide gas. It could be made use of from the sequestrated carbon dioxide. So we sequester carbon and then deal with our industrial process. So that way we can reduce carbon dioxide. So more and more of renewable power, VRE, that is variable renewable power, should be integrated to the grid for deep decarbonization of the power sector. Our topic of discussion today is grid flexibility solutions to enable more of RE integration into the power grid. So we'll consider some of the major solutions, grid flexibility solutions. They are the utility scale batteries, renewable power to heat, renewable power to hydrogen, supergrids, pumped hydro storage, virtual power lines, and dynamic line rating. So other small items are there which are of less importance. I am not including this particular session. So we'll consider each of these one by one. Utility scale batteries. Stationary battery energy storage system consists of utility scale batteries of capacity ranging from several megawatt hours to hundreds of megawatt hours. And lithium-ion battery is the most prevalent and mature technology. That's 100% of the battery energy storage system in use. They use lithium-ion batteries. Battery energy storage system, it increases the flexibility in power system, enabling optimal use of VRE sources like solar PV and wind energy. Batteries, battery, batteries have the advantage of geographical and sizing flexibility and can easily be scaled up. 90% of the batteries are of lithium ion battery. So the advantages of battery energy storage system is demand side flexibility solution. It's a demand side flexibility solution to regulate frequency. That is, frequency swings caused due to greater demand could be reduced by using battery energy storage system. Then flexible ramping can be made. Then black start services, that is, by utilizing battery energy storage system, we can start the uh, plan grid altogether black start mode. Then energy shifting and capacity investment deferral. That is, um, suppose if you want to have a better utilization, then if we need to increase the capacity, maybe a transmission line capacity or a generation capacity, it could be uh, deferred. The investment in that, it could be utilized for other purposes. And especially when we try to construct a transmission line or a generating plant, then we come across what is called NIMBY syndrome, that is not in my backyard syndrome. So whenever a capacity addition or line doubling, maybe single circuit to double circuit conversion, when utility wants to undertake, normally people in the, that is the landowners, property owners who are affected with line extension or line upgradation, they stop the process by engaging in some cases and all. So that could be avoided. So that public problem could be, that is, or public reaction could be avoided by using battery energy storage system to a limited extent. Then transmission and distribution congestion relief. So when systems are operating in full load, then there is difficulty in managing the system. Then unnecessary trippings will be there due to overloads and all. So, and we have today, nowadays we have under frequency, then rate of change of frequency tripping and all. So those changes can be, um, those problems, unnecessary trippings can be avoided, so that services can be provided maximum extent to the end consumers. Transmission and distribution congestion relief can be attained by using battery energy storage system. Battery energy storage systems are of megawatt hour nature. That is, in a grid level battery energy storage system. Reduced RE curtailment, that is, renewable energy, if it is produced in excess, that is, if the renewable energy produced is more than what the system can withstand, that is, what system can accept, maybe transmission line, suppose if it's getting overloaded, then we have to curtail the renewable energy. This happens especially in global situations, especially in China and all, where they have a lot of wind energy generators. Renewable energy curtailment statistics say 15 to 25% of the renewable energy curtailment occurs in China, and in US some 2 to 3% of is the average curtailment that they have to face in case of solar PV, solar photovoltaic generation. So such renewable energy curtailment can be avoided if we have battery energy storage system, so that curtailed, whatever energy is curtailed, renewable energy curtailed, can be stored in the battery and can be utilized for future use. So that way we can reduce the RE curtailment if we have battery energy storage system. Capacity firming can be made, that is, renewable energy because since it's a non-dispatchable power, um, we can have better firming of capacity if battery energy storage system is there to back up the renewable energy. Variability of the renewable energy can be smoothened somehow with battery energy storage system. Reduced reliance on diesel generators in microgrids. Microgrids normally, standalone microgrids, if they are there, then battery energy storage system can be used to avoid diesel generators. That is normally when the microgrid, that renewable energy is not there, that's due to intermittency or variability issues of renewable energy system. If it is not present, then the battery energy storage system, from the battery, we can have power delivered to the essential loads of the microgrid, so that the supply can be maintained with battery energy storage system. Technical requirements of battery energy storage system as regards hardware is widespread adoption of utility scale batteries in a power system, and software, battery management software to protect battery and act as a site controller to implement charging and discharging algorithms. The charge of the battery has to be monitored, and the battery management software has to switch off the charging once the overcharging has to be prevented. So overcharging has to be prevented, then charging has to be restarted once the charge has exhausted. So everything is being achieved with the help of battery management software. So these are the system requirement for battery energy storage system. So we'll come to the next solution. It's renewable power to heat. So here, what we intend is that whatever renewable energy that we produce has to be has to be converted into heat and stored in uh, a central facility. Maybe it is for district heating and all. It could be utilized. So, or it can be stored in the form of hot water and used in residential area. So renewable power to heat refers to technologies that use renewable energy to generate heat for buildings and industrial processes via heat pumps and electric boilers. Electrification of heating can help decarbonize power sector when the extra load is supplied with renewable energy and managed smartly. Power to heat systems can help integrate greater shares of VRE by using heat pumps and electric boilers as a source of demand-side flexibility in power systems. Power to heat systems, they help in reducing what the advantages of power to heat systems, help in reducing renewable energy curtailment, increasing flexibility through shifting of load, then storing energy on large scales. That is, the energy has to be stored in as heat in insulated containers and all. So then providing grid services via aggregators, increasing self-consumption from local renewable energy-based generation. So that is when RE is in excess, when renewable energy is in excess, we can have local renewable energy-based generation, and can be stored as the renewable energy can be stored as heat, and heat can be utilized elsewhere at some other time for district heating or such purposes where heat can be utilized. So key regions where power to heat systems, that is power to heat systems are normally employed in cold climate areas: Canada, China, Japan, US, and the Europe, especially Denmark, Germany, Sweden, Switzerland, the UK. Technical requirements of power to heat systems. Hardware, we require heat pumps, boilers for heating systems. Pipeline infrastructures are required for district heating systems. Sufficiently insulated buildings for effective thermal storage. That is, the building facade and all has to be lined with that wool rock wool, mineral wool, etc., for containing the heat or to insulate the whatever heat that has been stored in the building should not be released. So it should be insulated properly. Sufficiently dimensioned hot water storage industry, sufficient technical and economic feasibility thermal energy storage technology, metering equipment such as smart meters or devices built into storage systems required to provide real-time power consumption and production. Software requirement, optimization software for heat pump systems that can adjust consumption according to demand. Aggregation software with algorithms um, calculating the optimal operation of each unit. Real-time communication between the aggregator and hardware system. Distribution system management software to ensure reliability and safe operations. These are the technical requirements of power to heat systems. The next solution is renewable power to hydrogen. Hydrogen is considered now, it's going to be the future energy source. That is, energy, electricity as an energy carrier, uh, it can be stored limitedly in energy storage, battery energy storage system, etc. But hydrogen, it could be uh, manufactured from renewable electricity. It's called green hydrogen. Green hydrogen can be stored and utilized uh, maybe after a very long time. So, and it could be transported to places where renewable energy is not available. And hydrogen is said to be the most important energy carrier. It's more of importance, like, it can be used as I mean it is an energy carrier that could be stored and transported um, by using different means of transportation, and hence it may overcome perhaps the electricity sector and the electricity as an energy carrier. So converting VRE sources, variable renewable energy sources, to hydrogen via electrolysis can contribute to power sector transformation in several ways. We need to have what is called electrolyzers, electrolyzers which converts water into hydrogen and oxygen. It's the reverse of fuel cells. So electrolyzers split water into hydrogen and oxygen, and the hydrogen thus produced is collected, compressed, and in some cases, to increase its utility, it has to be converted to other uh, gases or liquids like ammonia, methanol, that is CH3OH, methyl alcohol, etc., to facilitate usage, transportation, and storage. And it could be utilized as an energy source. So if we manufacture green and ammonia from green hydrogen, it is called green ammonia. So the famous Haber-Bosch process is available to manufacture green ammonia, that is at a higher temperature, near about 700 degrees Celsius. When nitrogen and hydrogen are combined, it gives ammonia. So when hydrogen is sourced from green electricity, that is from renewable energy, what we obtain is green ammonia. It is as good as green hydrogen, um, and not much of the carbon content is not there. And at the destination, we can retrieve hydrogen if we want from the ammonia by using catalytic heating. We can retrieve hydrogen from ammonia and utilized. So or even ammonia can be used as it is in fertilizer sector and all. Ammonia is required as ammonia, and ammonia can be utilized as it is green ammonia. So uh, for manufacturing ammonia, we need not have coal and natural gas or oil fired to produce the heat for making that Haber-Bosch process or manufacture ammonia. Then, so converting VRE sources to hydrogen by electrolysis can contribute to power sector transformation in several ways. They are reducing VRE curtailment, long-term energy storage, providing grid balancing services via electrolyzer, and using green hydrogen as a fuel in other sectors, transporting and storing renewable power over long distances as hydrogen. And one of the important characteristics of green hydrogen is that, as an energy carrier, is that it can be transported and stored, and can be used at par with energy source. So it's an emerging energy carrier. In fact, currently we are undergoing, that is, we are um, deriving our energy needs from hydrocarbons. So we say it's hydrocarbon economy that is currently going on, and a shift from hydrocarbon economy to hydrogen economy is not that distant. So uh, maybe within by 2030 itself, so much of renewable hydrogen, green hydrogen is being planned, manufacturing facility and utilization. And various applications are also being planned in hydrogen economy. And by 2050, um, globally, the IPCC and the world community, they want to shift from the um, coal-based economy, hydrocarbon economy, to hydrogen economy and renewable power. And hydrogen will play a very important part in energizing or in electrifying our various needs. Power to hydrogen systems. So hydrogen produced by electrolysis of water by splitting it into hydrogen and oxygen. When renewable energy is used in the electrolyzer, hydrogen becomes a complementary carrier of renewable energy, that is green hydrogen. Hydrogen produced with excess solar PV or wind power can be stored for a later use as a fuel for hard to electrify sectors like transport, industry, and other sectors. So the hard to electrify industrial sectors are cement industry, refineries, petrochemical industries, aluminum industries, and iron and steel. And transport sector, all transportation, that is road transport, rail transport, shipping, aviation, everything, hydrogen can be utilized, provided the research community and the manufacturers, they have to have a common linkage. And the planners and policy makers, the countries, various economies, they have to properly coordinate with the manufacturers and end users, and policies must be made to utilize hydrogen as a fuel. And in proper form, if they use, then every sector, is every transport sector like aviation and all, are major contributors to um, this greenhouse gases. Shipping is also major contributor, and there it's very difficult to attain. That is, electrification is not that easy in shipping and aviation. Hydrogen provides a good solution. Hydrogen produced can be used as smart source to increase power system flexibility and help to decarbonize the overall economy. We have something called, that is in Western Australia, Australia's central region are all solar rich, is solar PV rich. So there, Australia plans to enhance their solar energy production. And in Western Australia, they plan to have a hydrogen, that is solar to hydrogen conversion. And hydrogen just produced will be shipped to Japan, where Japan is the consumer country and consume. They are building the port facilities to receive hydrogen from Australia, Western Australia. So that way, uh, that Western Australia, that is Asia, Australia energy connection is being established in that fashion. In fact, it was earlier decided in 2014 and all, it was decided to have an electric connection using HVDC cable between Western Australia and Japan. But later on, um, since hydrogen transportation, production and transportation is cheaper than electricity transportation, they have changed their plan to shift to hydrogen than to electricity, from electricity. Stored hydrogen may enable the efficient distribution of energy across regions, facilitating VRE consumption in areas where it's not available.
Down to it.
So,
no, thank you.
This is important characteristic of hydrogen. Green hydrogen, which can be generated where renewable energy is available in high quantities, can be stored and transported to areas where renewable energy is not available, or that way renewable energy utilization can be smoothened across economies. Power to hydrogen systems advantages: reducing curtailment of excess VRE generation. That is a common advantage in all solutions. Providing long-term energy storage, providing grid balancing services, supporting sector coupling strategies by increasing use of renewable energy in other sectors as a feedstock and as a fuel. So sector coupling may mean um, that is electricity is a sector, industry is a sector. So coupling electricity and industry, that is sector coupling. So here hydrogen can be used as a feedstock for certain industries or for power generation, and it could be used as a fuel. Enabling distribution of renewable power across regions and globally. Um, Microgrids and fuel cell applications, that is grid independence. That is, suppose if microgrid is not connected to the main grid, then with fuel cell applications and hydrogen available at the microgrid vicinity, we can um, utilize hydrogen through fuel cell to generate electricity and use in the grid, use in the microgrid. That is grid independence. That's total independence from the main grid. That is what is meant. Then hydrogen, one of the major advantage of hydrogen is its synergy between um, offshore generation, offshore RE generation, and transportation hydrogen. That is, hydrogen can be created, can be generated using electrolyzer um, from the renewable energy produced from offshore generators, wind generators, and then this hydrogen can be transported maybe by utilizing ship or of that nature without even connecting to the main grid. Then this hydrogen can be used in the steel sector, where our turbine blades, wind energy turbine blades are manufactured. So a total closed circular economy sort of item is possible in case of hydrogen, hydrogen and offshore wind synergy. Technical requirements of hydrogen, power to hydrogen system. electrolyzer technology to produce hydrogen from renewable energy, hydrogen fuel cells to convert hydrogen into electricity when required, conversion units to use renewable hydrogen and convert to methane and ammonia, hydrogen transport vessels, just ships and trucks, transport infrastructure, this repurposing or retrofitting of CNG infrastructure. Here, what we mean by repurposing or retrofitting is that retrofit, that is CNG pipeline, CNG infrastructure can be, uh, sorry, it's not retrotting, it's retrofitting. Retrofitting, by retrofitting, it is what is meant is that we have to change the valves and all, because if we add hydrogen into the CNG pipeline or CNG infra piping infrastructure, then um, what we end up is hydrogen blending. The process is called hydrogen blending. We can blend 20% of the 20% of hydrogen with CNG and utilize, provided we do retrofitting of the piping infrastructure. And repurposing means the entire CNG infrastructure can be converted to hydrogen infrastructure by using repurposing, where the compressor, that is for pressurizing compressor, then valves, turbines, everything, if they are, if, and even the pipeline, suppose if the pipelines are weak, then pipeline also has to be changed. So that way the entire infrastructure is repurposed for transportation of hydrogen. The CNG infrastructure is repurposed for transportation of hydrogen. That is called repurposing. So cost-wise, retrofitting is cheaper and repurposing is costlier. But anyway, repurposing is it costs only 30 to 40% of fresh infrastructure, fresh hydrogen infrastructure. Then storage facility of hydrogen in compressed and liquefied form. Liquefied form, hydrogen becomes a liquid only at 20 Kelvin, that is very low temperature, minus 253 degrees Celsius. And to maintain that temperature, to attain that temperature, to maintain the temperature is a bit difficult. But then in liquefied form, and has been properly insulated in aviation and all, the application requires liquefied hydrogen for 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 utilizing hydrogen in aviation sector. Now we have come to the next solution, that is super grids. Super grids, they are achieved by interconnecting regions or countries, continents with high capacity power transmission lines with HVDC system above 500 kV or UHVDC system above 800 kV power lines to transfer large quantity of power with greater controllability, lower losses, and increased flexibility. Then super grid offer increased energy reliability, higher availability of generation, decreased cost of electricity across regions, and is particularly relevant for higher integration of variable renewable energy and greater system flexibility. So that's one of the, that is grid. We are expanding the grid. It increases, grid increases, the size of the grid increases in a supranational function, that is in a supranational way. That is internationally grid increases. Suppose we have a national grid in India, we have national grid, and the SAARC grid is in the formation stage. That is, we are extending the grid with Nepal, Bhutan, Pakistan, then Sri Lanka and all. So SAARC grid is evolving. Then Europe, in European region, European Union is planning to extend their grid to interconnect Asian continent and African continent by their interconnections, Euro-Asian interconnection and interconnector and Euro-African interconnector. So that way super grid is evolving. So if a global super grid is evolving, then that means we can have better adaptability of renewable energy. That is, solar and wind will be available at some part of the globe every time. So if we channelize renewable energy, then if a global supergrid is forming, then that global supergrid will be capable of delivering the energy needs of the entire globe. And with the global interconnection, that is intercontinental interconnection, they are provided with HVDC lines, HVDC cable, under like submarine under HVDC cables are utilized for interconnection between various continents. Intercontinental connections are being planned with. Europe, I think, is taking a lead role to achieve the global supergrid. Advantages of supergrid. Transmission of renewable energy from resource-rich areas to distant demand centers can be made use of by using using supergrid, and flexibility can be increased. Reliability in the local grids also can be increased with increased interconnection. Then connecting two onshore points of the same country using offshore HVDC link. That is another advantage of supergrid, because that NIMBY syndrome, that not in my backyard syndrome and all, it creates a lot of problems in drawing transmission infrastructure through land. So if submarine cable is used to connect two onshore points, the same country, then that HVDC link can function as a bulk power interconnector, and it's an major advantage of supergrid. Technical requirements of supergrids. DC breakers, because HVDC stations are required for interconnecting onshore areas. So DC breakers, DC protection systems, HVDC cable, DC switchgear, AC DC interconnection system, inverter and converter systems, etc. So that Euro-Asia interconnector, connecting national electricity grids of Israel, Cyprus, and Crete, Attica, Greece through a 1,518 kilometer of HVDC subsea cable of 2,000 megawatts capacity. Work has commenced in August 2021 and started for completion by 2025. Similarly, another interconnector between Egypt and Europe, that is planned via Crete, Attica, Cyprus, Greece, through a 1,707 kilometer of HVDC submarine cable. Concrete encased submarine cable is used to connect to the onshore grid portion of the link. That is, the HVDC submarine cable is taken onshore through concrete encased pipe to connect to the main land grid. So here bulk power can be transferred without any regulation. That is, without any regulation, since there is HVDC line, high amount of current controlled, uncontrolled power, it's not uncontrolled, limited, quantity, this correct quantity, whatever quantity that we want to transmit, could be transmitted through HVDC line, unlike AC systems. AC systems, they have another disadvantage while using as undersea cable, that is the electromagnetic interference that is produced by AC. It plays with the navigational issues of vessels, that is ships and all going via sea, and the navigation problems will come. That is another big problem with the AC cable. So HVDC is the most apt interconnector for supranational interconnection. So the next solution is pumped hydro storage. It's a very proven technology that is in existence for a long time, pumped hydro storage. It serves as a giant water-based battery or energy storage facility, helping to manage variability of solar and wind. Pumped hydro storage can be used to balance the grid, complement other RE infrastructure, and facilitate effective supply shift. Pumped hydro storage has the ability to actively absorb surplus power from the grid, making it a more cost-effective flexibility solution than batteries, interconnections, and power to X, that is power to heat or hydrogen. The global capacity of pumped hydro storage is 161 gigawatts as of 2018, and to achieve a higher end need of fossil-free electricity, fossil-free power electricity sector, we need to have by 2030 300 gigawatts of one pumped hydro storage is required, and by 2050 325 gigawatts of pumped hydro storage is required. Here what is happening is that from lower storage level, um, water is pumped to upper reservoir, and that is during off-peak hours. And during peak hours, water is allowed to flow through the generating equipment, turbine and hydraulic system, to generate electricity and support the grid during peak hours. Innovations of PHS station operation, that is variable renewable energy and pumped hydro storage, they can be coupled. So if pumped hydro storage and variable renewable energy plant are located in the same site, then the first scenario comes: VRE and PHS as storage on site. Wind or solar PV or both are both installed. Wind or solar PV or both are installed in the proximity of pumped hydro storage facility. Then VRE technology integrated into the PHS facility. Here, floating solar PV is installed in PHS reservoir. That is, in the reservoir top surface itself, for solar PV, floating solar PV panels are deployed to generate renewable energy and used in concatenation with the PHS station. Services provided through innovative operation of PHS. Load shifting and reduction of RE curtailment. Frequency regulation can be made with PHS, and fast and flexible ramping. So as far as our power grid is concerned, any hydro-based generation is very fast in ramping the or meeting the flexibility of the load. Then black start, capacity firming when connected to an on-site VRE generator. Then reactive support with synchronous condenser operation. The same machine can be operated in synchronous condenser mode when not generating or pumping, and it could be utilized for providing reactive support to the grid. Then is a comparison of various storage technologies. High energy storage, the efficiency is 30 to 45%. Typical storage capacity is less than 1 gigawatts, and typical discharge times, it varies from less than 1 hour to 1,000 plus hours. And the maturity of technology is under research, development, and deployment. Batteries, that's battery energy storage system, 70 to 85% is the efficiency. Typical storage capacity is less than 100 megawatt and less than 5 hours the discharge time typically. It's commercialized in USA, UK, and Australia. Compressed air energy storage system, that is compressed air as a medium of storage of energy. 45 to 70% is the efficiency. Storage capacity is less than 10 megawatts and 5 to 100 hours typical discharge times. And it's also under research, development, and deployment. Flywheels, it's an in an under R&D stage. Here, the inertia of the flywheel is utilized to ramp up the generation. Here, the efficiency is 85 to 100%, but the power could be, that is, it's only less than 1 megawatt, and the time is also very less than 30 minutes under R&D stage only. Pumped hydro storage, 70 to 85% is the efficiency. Typical storage capacity is 0.1 to 1 gigawatts, 10 to 500 hours, and it is a commercialized technology. Next solution is virtual power lines. VPLs or virtual power lines allow large-scale integration of VRE without grid congestion or pre-dispatch, avoiding any immediate need for large grid infrastructure investments. VPLs provide 3 gigawatts of installed storage capacity worldwide as of now. Global needs of network investment deferral could reach 14.3 gigawatts by 2026. Australia, Italy, France, and the US are piloting virtual power lines to reduce renewable energy curtailment. Virtual power lines result in reduced curtailment of VRE due to grid congestions and offer faster and more flexible solutions compared to network strengthening. So I've drawn a small picture of VPL. This power generation, then grid element is there, load or peak demand. So grid element can be a transmission line. So when power generation is in excess, that is when RE curtailment has to be undertaken otherwise, then the supply side storage, this is a battery storage system, bulk storage system. Then there we have a demand side storage, another bulk storage system. So the supply side storage can be charged when power generation is in excess, and there is and the grid and if the load demand is less, then demand side storage can be charged when load demand is less and the grid is not overloaded. That is, the transmission line is not overloaded. That is, if grid can safely transfer the power, and if load is less, then demand side storage can be charged. So, in the absence of variable renewable energy generation, then the demand side storage can serve the load of the peak load of the load. So peak demand of the load can be served with demand side storage. And in the excess, when generation is in excess, then supply side storage can receive all the generation and store it. So that way, RE curtailment is reduced, and grid expansion, that is a big problem that we normally face in utility level, that could be reduced. So we have VPL constituents. VPL consists of utility scale storage system connected to grid at two key points. One on the supply side, storing surplus generation from renewables that could not be transmitted due to grid congestion. Another on demand side, charge whenever grid capacity allows and then discharge when needed. Network upgrade challenges and opposition from local community can be avoided. Here again, that 100% extra capacity addition can be done if we convert a single circuit to double circuit, and we can increase the reliability of the system, of the transmission system, if we convert to single circuit or double circuit. But then the local community opposition may be high, so that BPL, if we incorporate, it is an efficient mean, an efficient solution for renewable energy integration. Then the last in the solution that we are going to do is dynamic line rating. Dynamic line rating reduces congestion on power lines, optimizes asset utilization, improves efficiency, and reduces cost. Permits DLR permits increased solar and wind penetration, reduces VRE curtailment, and makes power generation and dispatch more cost effective. DLR implementation has yielded 6 to 14% of increase in ampacity in 84 to 91% of the times. Several transmission system operators in Europe are implementing DLR. In KSEB Limited, under Thodupuzha Transmission Circle of KSEB, we have a DLR implemented in 66 kV Valathope Kattapana corridor. Features of DLR. DLR refers to the active varying of presumed thermal capacity for overhead power lines in response to environmental and weather conditions. That is, the static line rating is decided by the temperature rise in the conductor and the thermal overload limit of the particular conductor. So when the wind blows, or when the temperature, ambient temperature comes down, the temperature that is produced by heating effect of the conductor to flow of current is cooled by the wind or ambient temperature, low ambient temperature. So that condition, climatic condition, can be utilized to increase the load of the line, thereby deferring a capacity addition. That is the DLR, essence of DLR. DLR is done continually in real time. That's monitoring is done continually in real time based on changes in ambient temperature, solar irradiation, wind speed, and wind direction, with the aim of reducing grid congestion. DLR enables better use of existing grid, allowing maximized VRE integration by taking advantage of shifting weather conditions and their effects on a power line's thermal capacity. A line's thermal capacity will be higher if it is cooled by wind or when temperature drops, allowing more energy, more electricity to flow through the line. So what the factors affecting ampacity of a particular line? So it is the physical electrical contributions, this is the line current, sag and tension, physical and electrical properties of the material and construction of the conductor, then insulation. Then weather factors, they are wind speed, wind direction, solar radiation, and ambient temperature. DLR offers many applications and benefit to power system. It reduces congestion in the power system, optimizes asset utilization in a safe manner, results in additional income from existing generation assets, improve cost efficiency of lines, avoids investment in new lines. All these entail in lower prices for consumers, faster integration of DERs, and greater power system integration of VRE. DLR can contribute to overall system planning and enhances grid resilience, key to maintaining security of supply. So this is a case study with 32-kilometer ACSR line with static line rating of 787 ampere. That's decided by thermal overloading capacity of the conductor at 40 degrees Celsius. Zero wind, changes in ampacity is as given in the table. Features ambient temperature. If on 2 degrees Celsius fluctuation in ambient temperature, the ampacity change is plus or minus 2% capacity. A 10 degrees Celsius drop in ambient temperature yields 11% increase in capacity. That is, the SLR of 787 gets increased to 874 amperes. That's the new ampacity in case of 10 degrees Celsius drop in ambient. Solar radiation, clouds shadowing, plus or minus only few percentage. Then middle of the night, in the absence of solar, the solar heat contribution due to solar is not there. Then plus 18% capacity enhancement is obtained. That is, instead of SLR, in place of SLR 787 amperes, we have 929 ampere as the new ampacity, enhanced ampacity. Then in the presence of wind, when wind speed it increases by 1 meter per second, if the wind is blowing at 45-degree angle to the conductor lay, then plus 35% capacity is achieved, 1060 ampere instead of SLR rating of 787 ampere. And if the wind is blowing at 95-degree angle, plus 44% ampacity enhancement is obtained. That is, instead of SLR of 787 ampere, we will get 1130 ampere. The DLR implementation requirements: line identification, sensor installation, data communication, data analytics, computing and temperature forecasting, validation for improved visualization, self-contained line monitors encompassing auxiliary power, communications, and all measurement sensors, SAC detectors, weather stations, data loggers, communication devices. We are coming to the last slide of my presentation. Tailored algorithm, that is software and communication requirements, tailored algorithm for transmission capacity calculation for each line, data logging software to record and analyze data from DLR equipment, data analysis software deploying by TSOs to analyze data generated by DLR system, which must have interoperability with softwares invoked by system operators, forecasting algorithms complemented by AI tools to improve DLR performance, minimizing weather forecast and operational errors. Communication protocols, 4G or 5G enabled DLR equipment that can be used for real-time relay of data to system operators. So I've come to the end of my presentation. So please, any questions or discussion we can have.
Though somebody can read the questions in the chat box. Hello.
Hello, yes, sir. Sir.
You can read the questions in the chat box.
Yes, sir, I will read.
No questions there in the chat box?
No, sir, no questions.
Okay. Let me have a question, Anil sir. What
Yes,
is
sir,
the
yes,
what is the possibility of pumped hydro at Idiki?
Idiki, actually, it's a policy decision. Because since we are coming to we are in a national grid since 31st of December 2013. That is, India is operating as a national grid. So the power system thinkers, planners, and all, they have to implement. They have to make a policy to implement decisions. It's possible. It's possible, and it's very much possible.
I think there is plan for the floating solar at Idiki. It is
Yeah.
paper, yeah.
That's also there.
Okay. But another thing is, the energy storage in the solar is a must, because solar cannot grow without energy storage.
Yes.
So and definitely KSEB will be planning schemes with energy storage, especially maybe the hybrid solar power systems.
Yeah. because hybrid systems, if we have, then wind and solar, they can support each other. That is, that synergy can be obtained.
That is one type of hybrid. Other hybrid, the instead of grid connected inverter, you can have a battery also along with the grid connection.
Yes.
Yeah. That is allowed now.
IBR facility. That is
It
battery.
is the grid connected inverter goes off when the grid is also down. But in case of a battery, also along with the grid connected inverter, which is called hybrid inverter, it will not go off. It will continue to supply the load to the essential load connected to that.
Okay.
So you will not lose the solar power.
Okay.
Actually, pumped hydro was already there in India. I think almost 8,000 megawatt is there, but that was not used for this solar.
Yes.
So in a thermal power station, when the PLF is very low, they pump water, and in the evening when there is a peak load, then they run the hydro.
Yeah,
that is already there.
Yes.
Sir, one question, sir. I'm Bobby Philip from PS. With the increased penetration of solar rooftop plants, does the KSEB has any plan to install such battery storage systems in any area of Kerala, like where there is large penetration of solar?
Because I am a retired person now, and so what KSEB say, I cannot say, because that is decided by government and Ministry of Power, everybody. So I cannot say it now, because such things will have to come to sustain in the. That's the need of the hour. This battery energy storage system has to come for integrating renewable energy to a certain extent. So basically that's VRE sources. If you want to integrate, battery energy storage system has to come. So that way it is the need of the hour. So it's a do or die situation.
Okay. Anyway, you support that idea.
Definitely.
And one more doubt. You talked about that dynamic load rearrangement and load.
Yeah.
So that is 66 kV.
Yeah.
And when there is that current change is there, then what about the voltage regulation? Will that be affected?
No. Voltage, it's not. That is connected to the grid. No, voltage is not affected.
Okay. So it won't be an issue there.
Because current that is supported by various software systems. That is so many inputs are there. That is
Phaser.
Phaser measurement. Then so many transducers are there. Real-time visibility into the system for the transmission system operator is required for DLR software, through DLR software.
Okay.
So many things has to be coordinated to attain that or to achieve that DLR objective.
So it is a well controlled process. Okay.
Yes. And implementation cost is also there. Millions.
Yeah.
So is there any more questions? Please feel free to ask or drop them in the chat box. And also we'll be sharing a feedback form for the session in the chat box. Please fill it out.
I think before going for the vote of thanks, let me have a few comments. I think Anil sir has almost touched almost all type of energy storage, because solar is the future of renewable energy in the world as such. Because among many energy storage, many renewable energy sources, solar is predominating. And as he was telling about the hydrogen fuel, which is the future of the energy storage. So we have electric vehicle on the road with the battery powered. maybe after 10 years, you will be having it is fuel cell powered electric vehicles. So all these things are the need of the hour. It is all coming one after another. And it was a very informative session, which has given us many new informations about the storage, dynamics, regulation, etc. It was really good. And I think if it is no more questions, perhaps Bobby sir can go for a vote of thanks.
Okay, sir. So, as it has been a very nice session, as we have been listening to it. He has covered a wide area. I mean, he has actually started with the beginning of such renewables and has gone through the developments and also the future trends was also actually came into the picture. So, in fact, he has rightly pointed out the right shift towards that hydrogen fuel-based system, hydrogen fuel and electrification that is going to come in the future. And he has covered almost all the issues with the renewable energy in the advantages and disadvantages. That too, he could limit it within 1 hour. So that is a kind of magic he has done, and he has given our overview. And in fact, from a layman point of view, and as an expert and as a student, everyone was able to understand some kind of, they could put some overview of the topic. On behalf of IEEE PS Kerala chapter and IEEE Education Society Kerala chapter, and of course KSEB Indies Association is joining with us. Our participants, on behalf of all the participants, I thank him for coming over here and presenting a very nice session. Thank you, sir. I thank all the participants also for being here, and thank the other sister societies of the HPA for coordinating the activities, and also I thank the Engineers Association for coming forward with such a cooperation. And thank you, Krishnamurthy sir, also. He has been with us in many programs. Thank you, sir.
Thank you, Anil sir. Thank you, Krishnamurthy sir. Thank you. Bye.
Thank you, sir. Thank you. Bye.
Bye.